Hello friends, today I'm back again with a new video that will show you guys how to install Sulley as a application level fuzzer. In addition to that, I also plan to show you how to write a simple Sulley script. This script is supposed to give you sort of a background with respect to how Sulley has created its primitives, its blocks, and the various other variables that Sulley uses. Sulley technically is an application level fuzzer that allows you to fuzz usually networking related applications, but can also be configured to fuzz local applications. So this is sort of a quick introduction with respect to how to install Sulley, and then in addition to that, some information about Sulley itself, and then a small Sulley script that would show you how to use Sulley to actually fuzz the application. So to begin with, I'm going to quickly keep this document open in front of the people who want to view the video. This is basically the context that has been taken from one of the books that I was going through, which is related to GY Python. And basically what you need to do is download the Sulley folder that has been provided in this specific URL. It's the nostars.com/ghpython.html. In addition to that, what you want to do is install Sulley 2.5, I'm sorry, Python 2.5 in your folder. So what I'm going to do is I'm going to go quickly to my installation and show you how it's done. So install Python 2.5. You can install WinPcap. Once WinPcap is installed from this specific URL, you would like to install Impact, which is a packet decoding and creation library also written in Python. And then PCAPI is a Python interface. So basically both of these need to be installed. So once you get the PCAPI, you can install it from the specific URL. Once that is completed, you can get the impact library from the impact stable.zip, and at that point of time execute the following, which is python.exe setup.py.install by going into the impact folder, and that should help you to install the requirements. So let's quickly go through the requirements again. Download the Sulley folder from this specific URL. Copy all of the material that has been downloaded to this specific directory. In my computer, this will be the installation directory. It's basically moved into side packages. It's the core of the Sulley. Then WinPcap. After that, PCAPI and Impact. PCAPI can be downloaded from this specific URL, and Impact can be downloaded from this specific URL. Once that is done, install Impact this way, and you should be done with respect to installing Sulley on the machine that you plan to use. I also have all these folders sort of created out that I plan to provide to anyone who is interested. My email address would be tomindian84@gmail.com. So if anyone is interested in receiving these specific packages directly as zip files, I can provide those as well. But this is what basically the folder installation would be looking like. So that's pretty much it about installation from Sulley's perspective. Next, we will also install PyDebug. PyDebug is an additional sort of utility that can be used to install and run PyDebug components. Basically, it helps to perform Python debugging rather than using a Win debugger or only debug. It's possible basically to have a Python script debug your application while it's running. So in case if you find faults using fuzzing, they can be also identified. So again, the same way you'd need to have Python 2.4.4 installed. Once that is done, you have to get the C types. Again, the URL has been provided. Once the C type has been provided and installed, you can download PyMay from the specific instance, get the source of PyMay from there. Next step would be to copy PyMay into the specific folder, run the installer. Once it's complete, that's pretty much it. Then you can go in echo in the Python shell, and basically in Python shell do the specific thing, and you should be able to see all the PyDebug inputs. Again, the same sort of logic I'm applying is that I'm gonna have this PyDebug install folder as well, and if somebody needs it directly to be obtained from me, they can contact me at the email address that's tomindian84@gmail.com. That's pretty much it for installing Sulley as well as PyDebug. Now let's quickly go over a Sulley script. This Sulley script has been created to sort of fuzz a local application that runs WAV files. WAV files are basically music files or MP3 files, similar to MP3 files basically, that can be run by your music players. Usually every WAV file is composed of an RIFF header followed by a wave, the length of that specific the file, followed by the wave header, followed by a format chunk and a data chunk. The details of looking at a wave file can be obtained from the sonic.com. There's a website which basically allows you to look at how the format of a wave file is constructed. There are a lot of other format chunks that are also present, but I'm just going to fuzz using the basic two chunks that are required. So technically, every Sulley installation every Sulley script usually starts using an s_initialize. This is basically a global variable that allows you to define what your fuzzer's name is. So in this case, I'm naming this to s_initialize var, which is a global variable. The Sulley is very similar to using Python. You can use Python constructs, so I'm using a Python construct if followed by s_block_start. This is again a Sulley construct. What I'm saying is that Sulley allows you to create chunks of data, so that way you can separate them for understanding, as well as that way you have a variable value that has a chunk of data. So let's look at an example of a file. A simple file would be something like this. So this is sort of the header of a wave file. In this case, if you look at it, it has RIFF written on the right side, which is basically what the definition or the magic version of the file is, followed by the length, which is 4 bytes, followed by wave, which is another sort of subtype ID for RIFF, followed by the very first chunk, which is the format chunk, which has FMT. The format chunk consists of another 16 bytes followed by the length. So format itself with the header followed by a length of 4 bytes and followed by another 16 bytes. The 16 bytes have different variable values, which I'll explain over as we go over the Sulley script. Then it is followed by the data chunk, followed by the length of the data chunk, and finally the actual data in the data chunk itself. The goal over here is to sort of fuzz a few variable values. So Sulley is an intelligent mutation fuzzer. So the way you do is you define the grammar of the protocol. In this case, rather than the protocol, we're defining grammar for the file format. So the file format is that this will be one of the chunks, followed by this chunk, followed by the data chunk. So that's what we are trying to create using the Sulley grammar. If we look at it, the very first chunk is consisting of RIFF. keeping the value s underscore static. So Sulley provides different primitives. There are 4 primitives that are primarily used. S underscore static, which means this value is never going to be first. It's always going to remain static. There's s underscore string. The s underscore string basically allows to insert any sort of string variables or string values. Then in addition to that, we also have the s underscore short, which is which would be a 16-byte, a 16-bit or a 2-byte integer variable, and s underscore byte, which is 1-byte integer variable, s underscore word, which is basically a 4-byte variable, and s underscore double word, which would be an 8-byte variable. So these are the primitives that are provided basically in a Sulley. So if you can look at it, this is the very first one that I've used, which is s underscore static, which means that this value does not need to be fuzzed. A lot of file formats always have magic version numbers or magic headers. Usually they expect the program, when it runs, expect that these specific headers are present. So that's the reason you don't want to change that. The next one is s underscore sizer. The s underscore sizer is basically something that calculates the size of a specific block. So in this case, what we want to do is indicate that I want to calculate the length of the format underscore data, which will be consisting of the wave static value followed by a format chunk followed by a data chunk, if you look at it over here. So the s underscore sizer sort of helps you to calculate the size of the data chunk. So that would end the first block, which has a RIFF. Similarly, the next one is a format underscore data chunk, where the subtype ID has been included. Basically, we wanted to have the size of the rest of the packet, excluding the RIFF and the 4 bytes for the size provided in the RIFF chunk. So that's the reason we have included this underscore static again wave. Now again, this is a static value which remains static, so the same explanation goes here. The next is the format chunk. In format chunk, what we have done is basically have a s underscore static, which indicates that this is a format chunk. The very first value after that is the sizer of the format chunk itself again. So that's the reason we have the format data. The next block is the format data, where we have the very first variable, which is a compression code, which is a 2-byte variable, followed by the number of channels, which is again a 2-byte variable, followed by the sample rate, which is a 4-byte variable, and followed by average bytes per second, which is 4-byte variable, and the s underscore short again, which is a 2-byte variable, which is block aligned, and then significant bits again, which is a 2-byte variable. If you look at it, I've kept the attribute fuzzable is equal to false. Basically, I don't want these values to be fuzzed, as some of these values are expected by a program, and if you fuzz them, there's a possibility that you will miss the other exceptions that could be generated if the file has actually got processed by the player correctly. Once that is completed, we basically finish up with the s underscore block and for the format data, and then finish up with s underscore block and for the format block. Once that is completed, the data format is very simple. It basically expects a static header value, which is the data, followed by the size of the data, and then the actual data. I have basically included a static variable. This is something that I came across when I was trying to look at the different wave files, and it seems like this is sort of a header variable or header value before the string. It's not necessarily required for every player, but I did observe that this was required for one of the players that I was trying to fuzz with. So that is something that you would have to identify, but basically in a generic sense, you won't need this s underscore static variable. You would be requiring only s underscore string, which means fuzz the string, and then we basically end this data and the data variable, and then finally the format data, which consists of the overall value. I've also added an s underscore static at the end, which is basically null bytes. This was also basically observed at the end by me. Finally, we basically look at the total mutations. This basically function from Sulley indicates how many mutations it's going to create based on that. And then finally, we use the s_mutate function, which goes in a while loop. So until there are a number of mutations exist, we're using Python right now to basically open up a test file and then basically do an s_render, which basically throws a value. Now, since we are doing it in an f.write, these values are getting thrown into a file that's created, and that's how you basically create the mutations for local file fuzzing in this case. So that's pretty much it for the Sulley itself. Um, again, just a quick look at the whole file. There's not a whole lot different than a regular Python script, but basically you can look at the Python installation of the Sulley, and it's very simple. If you go into the Sulley, it basically has blocks, instrumentation, PDRPC, primitives, sessions, and SEX. The sessions is basically for an external connector. So if you are trying to fuzz like a network service, then that's where the sessions would be useful. I would try to show this as well to you in another file, which basically does network level fuzzing. The primitives is where you have the variables such as the block, the string, the s_static being defined. The pdrpc.py is a file that actually has the binary protocol that Sulley uses when it fuzzes network variables or network services, and so on. So very simple, very nice fuzzer that's been created. It hasn't been updated in a very long time, but it still works primarily pretty good for the basic installation that has been provided. So let's go and try to create this Sulley fuzz file. So I'm putting my fuzz files over here. So what I'm trying to do is run the Python, from the Python 2.5 folder, followed by the name of the Sulley file, which is wave.py. I've calculated total mutations, so it says there are 1356 mutations, and so it would create basically 1356 files in your folder. This is my folder where it should create the files after it's done. As we can see, the files are created now. I'm waiting for the Sulley installation to complete its iteration. Once that is completed, I would like to show you how basically you can use another binary that has been provided to me, which allows basically to identify exceptions that are generated by fuzzing. So in addition to using Sulley for local file applications, you basically need something that can monitor your target. So in this case, I'm trying to fuzz a K-map. I'm sorry, a KM player. This is sort of a player that I had obtained from an exploit DB script. Seems like this is susceptible to sort of an integer division flow. Let's see if we can identify that using Sulley. So what we intend to do is use an additional binary called crash.exe. Basically, it is a binary that monitors your target, in this case the KM player, and what we provide to it is basically the path to the binary, the number of milliseconds that it should wait, and then the argument, which would be in this case the WAV file. So what we do is create a for loop using Windows shell scripting. So we use basically a for/l, and in this case I'm just iterating over the 10 wave files that I have, but you can basically iterate over 1356 wave files if you'd like to. And basically what we do is call a do loop, which in this case would forward the crash, followed by the path to the KM player, followed by the number of milliseconds that it should wait. So this value kind of varies from different applications. I usually keep it a little bit higher because a lot of times the applications need a large amount of time to actually load up, and you don't want to miss, in that case, the exception, because If you keep like a smaller number, such as for example 3000, that means it will only wait for 3 seconds and then kill the process. So as opposed to that, you would want it to actually have run for a little bit longer. This obviously delays because you're technically waiting for 8 seconds with every click. So if you have 1300 files that it has to go through, every file would be opened every 8 seconds. So you can do the math. So that would be the amount of time that you would have to wait for all the scripts to get over. So let's go through our script and let's see if Sulley can basically identify this integer division. So it's trying to open up the very first test 0 dot, and it doesn't seem like it's crashing at this point of time. So it indicates that it process terminated normally. And looks like the second file itself caused the integer division. It says the divide by 0 and then basically has an EVX value. So it seems like the KM player crashes with the very second variable itself, or the second first file itself. So it looks like we have identified the integer by division variable, and just to make sure, let's try this again. What I plan to do is basically use only debug and make sure that that we are not getting a false positive from the crash.exe, so just making sure about that. Letting only debug load it up. And so the KM player has been loaded up now. I'm going to take the second file itself. And wait for some more minutes. And looks like it did crash. It seems there's an integer division by 0 if you look on the top bottom left. So yes, we have been able to identify the same variables using the Sulley file. Let's look in the hex editor. What was the reason for it? Let's compare this with quickly with the original test0 wave.file. And if you look at it, I'm trying to see if I can find it. So this is there. Yep, there's a difference of these two last variables. If you look over here, these two variables are a part of the RIFF structure that we had defined. They are basically these two bytes. This is the block align and the significant bits per sample. It seems like by changing the value from original 00 in the test 0.wave, if we change the variable value to 01, it seems like it causes a crash. So there we go. We have been able to identify an integer division by 0 using Sulley very easily. That's pretty much it. Thank you.